Hello everyone, this is Yangchenla Bhutia of Namche Government College, bearing a roll number 21NS0164 of BSc Second Sem Physics. First of all, I would like to thank our physics teacher Dr. C.P. Khatiwara sir and our entire physics department for giving us this golden opportunity to present a video on those topics as I had the Young single slit experiment. Okay, now let's get started. So before starting our video, let us see what are the topics we're gonna discuss in this video. Okay, first of all, we are going to discuss the introduction part, the principle, the theory, single slit diffraction, derivation, some advantages and some application. And at last we are going for the conclusion part. So now let's see the introduction part. Thomas Young double slit experiment performed in 1801 demonstrates the wave nature of light. Thomas Young, an English physicist, physician and Egyptologist, he worked on a wide variety of scientific problems and also revived the wave theory of light. Number 2. In this experiment, monochromatic light is shown on two narrow slits. You can say it as S1 and S2. Point number 3. The waves, after passing through each slit, superimpose to give an alternate bright and dark distribution on a distant screen. Point number 4. This is the last point. All the bright fringes have the same intensity and width. Okay, now moving towards principle. Here are some principles. Point number 1. According to Huygens principle, when light is incident on the slit, secondary wavelets generate from each point. Point number 2. These wavelets start out in phase and propagate in all directions. Point number 3. Each wavelets travel a different distance to reach any point on the screen. And at last, point number 4. Due to the path difference, they arrive with different phases and interfere constructively or destructively. Okay, now we will see the theory part. Okay, theory. Okay, when light is incident on the slit, secondary wavelets generate from each point. Now, before going to single slit, we have to know what is meant by diffraction or what is the definition of diffraction. So, diffraction. It is defined as the bending of light around corners such that it is spread out and illuminates areas where a shadow is expected. Okay, now there are two types of diffraction. Number 1 is Fresnel diffraction and number 2 is Fraunhofer's diffraction. Now let's see their definition. Okay, number 1, Fresnel diffraction. It is caused by the light from a point source. In Fresnel diffraction, the incident and the diffracted wavelength are spherical or cylindrical. Now, Fraunhofer's diffraction. The incident and the diffracted wavefronts are both planes. The incident and diffracted beams are parallel. The source and the screen are in infinite distance from each other. Okay, now let's see single slit diffraction. Here is the definition. It is defined as bending phenomena of light or diffraction that causes light from a coherent source. Okay, now what is coherent source? Coherent means when two monochromatic sources which produce light waves having a constant phase difference. It is known as coherent. Okay, from a coherent source to interfere with itself and produce a distinctive pattern on the screen called the diffraction pattern. Okay, now you can see here the figure of the single slit diffraction. So here you can see a monochromatic source of light. So please note that the source should be monochromatic. That is of the single wavelength. So here is the incoming monochromatic light source, as it is known as also laser. So here it had been, the light waves have been emitted by the source. The source is monochromatic source, and we had placed a single slit, two single slit, and a screen at the distance. So here the light waves have been diffracted by the slit. These are the waves diffracted by the slit, and at the screen we are going to get a fringe pattern or a diffraction pattern. So here we are going to see a fringe pattern on a screen. So here some of we will here we are going to get some bright fringes, some dark fringes, and this is a central maxima where the intensity of fringes will be maximum. The maximum point of intensity we are going to get on central maxima as compared to this both side. Here you are going to get a bright fringe at a maximum point. So as we know, so this was the explanation. This was the brief explanation of the single slit diffraction. Now I am going to explain the calculation part, as we should find a path difference of the waves. Okay, now let's take a two single slit and name it as A, B, and their width, say it as small letter A, and let place a screen. This is a screen at a distance D from the slit. So this is the whole diagram that I already drawn it. So here you can see AB is an opening point and this small letter A is their width. O is a point on a screen at distance D such that the waves from A and B reach at the same distance and at same phase. And this this O is a central bright. Let us consider a point P. This point P is a point at elevation of the theta, as we had took the perpendicular line from the A and name it as N. As you can see here, the length of AP is less than the length of BP, and you also can see here that AP is equals to NP. And the distance from OP, let it be Y. And as we know that the distance from the slit and screen is denoted by D. So now we should find the path difference between two waves from A to B. We are going to find a path difference of the wave between A and B. So here is the calculation. Okay, now we are going to take out the path difference between waves from A and B. So path difference equals to okay, now path difference of we are quoting the path difference between waves A and B. Okay, now the path difference equals to BP minus AP. BP minus AP. So the path difference equals to BP minus, as we know that AP is equals to NP, so we can write NP in place of AP because AP is equals to NP. So path difference equals to BP minus NP, so we are going to get only Bn. So your path difference is going to be Bn. Okay, now we got the path difference that's equals to Bn. Now we should find the value for Bn. So while finding value of Bn, we had to look at the triangle ABN. So in triangle ABN, I'm going to draw the diagram for the A. This is B and this is N. You know, this is a perpendicular line and this is the angle. This is called theta, and AB, here we have seen the AB is given by a small letter a, and we know that the opposite side of the perpendicular is always hypotenuse, and this is perpendicular. Now we should relate this both perpendicular and hypotenuse by some relation which is given by sine theta. Sine theta equals to P by H. So we are going to get sine theta equals to, here we are going to get perpendicular, this is our B, and our H is hypotenuse is going to be a small letter a, because this here you can see the width of AB is small letter a. So the value for your Bn, okay, the value for Bn is going to be a sine theta. Now this will be the general formula for the path difference of Bn, or the value of the Bn. As we got the value for Bn, now we are going to look for the condition for secondary maxima. It is also called a bright fringe. So okay, we observe that P is a bright point when path difference is 3 lambda by 2, 5 lambda by 2, 7 lambda by 2, and so on. So the general formula for the bright fringe or for the secondary maxima is as given as a sine theta equals to 2n plus 1 lambda by 2, whereas n is equals to 1, 2, 3, and so on. This is the general formula for the bright fringe. And the condition for okay, the condition for secondary minima, also known as dark fringe, okay, here it is. We observe that P is a dark point. P is a dark point if path difference is lambda, 2 lambda, 3 lambda, and so on. So here, and the general formula for the dark fringe, for the all those dark fringe, is given by a sine theta. As we use the sine theta, will give you n lambda, where 1, 2, and 3, so on. This is only for the secondary minima, which is also known as dark fringe. So now we got the path difference, we got the value for the path difference, we got the general formula for the bright fringe, and also the general formula for the dark fringe. Okay, now we will see some advantages of diffraction. As we already got the general formulas for all those things, so we are going for the advantages. The particles of medium at both corners of the slit act as a point sources, producing circular waves from both edges. Point number 2. Light passing through a single slit forms a diffraction pattern. And here are the Some application given: CD reflecting rainbow colors as holograms, sun appears sun appears red during sunset. And at point number 4, bending of light at the corners of the door, spectrometer, X-ray diffraction to separate white light. Okay, this was all about the single slit. As we learn, or as we discuss some theory principle about the single slit, or as we call it, diffraction pattern. So this was all about the Young single slit experiment, and now I'm going to end my video here. So thank you so much.